Hi there, actually I'm Endre, this is Dominic, and welcome to this talk on memory tracing. We also like to thank a couple of people who have contributed to the project through ideas or code. This is Jonas, Damien, and David. Let us first start by introducing the idea of memory tracing, and then go into details later. It's a memory analysis technique, so let's start with what we would call traditional memory forensics, which you see in the upper half of this slide. In traditional memory forensics, you have a piece of, let's say, malware or executable running on a system. Then it's in memory and keeps changing its data or code. And at a certain moment in time, you're going to take a memory snapshot, which is shown here by this red bar. Okay? And then you go on using tools like volatility and other tools to analyze what's going on. What we do in memory tracing is related but slightly different. We also have some malware or a program running on the system, but instead of taking just one memory snapshot, we take like hundreds. In fact, you take up to 100 memory snapshots per second. Okay? So what you get as an output is a collection of many memory snapshots, which we analyze later with some tools. We call this collection of memory snapshots a memory trace. Okay. The next question is, of course, why is that possibly useful? And let's develop some intuition for that first. So you see here by these colors that a piece of malware keeps changing in memory. And the idea of memory tracing, of course, is to capture as much state of a piece of malware as possible. So if everything goes fine down here, you see we get the red malware, the green one, the blue one, etc. That's kind of the idea behind it. We certainly get the comprehensive state of a system through a memory trace. And there's another motivation actually for doing that. There's lots of transient data in memory. I mean, be it obfuscated data or code which keeps changing at runtime. There are certainly crypto keys and buffers which are also transient. Transient means short-lived, and other data. So the idea would be really to get that data. What we're going to show in this talk is that memory traces can actually be used for reverse engineering malware, at least some aspects of malware. And we're also going to show that some parts of this analysis can be really automated. And the other parts which cannot be automated, is also helpful. The idea there is, let's say we find something interesting going on in snapshot 2315. Then the analyst can take the snapshot and work from there manually using standard tools like WinDebug, IDAPRO, whatever he or she likes. Okay. Good. So let's have a look at the systems perspective of our tool. It's a dynamic analysis system, so we have a piece of malware, you get it onto an analysis machine, let it run there for whatever time, a couple of minutes. This machine has a component which does this whole memory sampling, and then it outputs the memory trace, which is this collection of memory snapshots. We move these memory snapshots over to another system where the analysis tools reside and do the analysis. And in a nutshell, the system is made of two components, the acquisition component and the analysis component. And in this talk, we're going to start with the analysis component. We're going to show you a couple of features for doing analysis, actually. And then we show you a demo of an actual malware analysis. That's kind of the most important part of the talk. Towards the end of the talk, we look at the acquisition engine, and we're going to talk about how it's implemented and how it works. Okay, so let's have a look at a couple of analysis features. The first one is the simple one. It's called memory timelines. And the motivation is the following. Often you start a malware analysis with a sandbox by running the malware on a sandbox, which gets you a sandbox report, which contains information like files being modified, processes started, DLLs loaded, all these things, registry modifications. The sandbox reports often give you an overview of what's going on, and you get kind of the big picture. Okay. And just out of curiosity, we are wondering if we can reproduce a sandbox-like report from a memory trace. And that actually is pretty easy to do. And this slide shows how we do it. What you see on the upper half here, in this picture here, You have the x-axis, which is time axis. These are the snapshots which are taken, okay? And the y-axis is physical memory. And the approach is really simple. What we do is we use volatility to extract system state from each of these snapshots. We extract like running processes, DLLs being loaded, network stuff, all these things we're interested in. And then from that information, we derive events like process creation, process termination, DLL load, all these things which you have with traditional sandboxes. And this can be done actually quite easily. What we do is simply we diff these outputs. So for instance, if you have a DLL in this memory snapshot here, and it's no longer in that one, the event we generate is a DLL unload event. Okay, that's very simple. And using that approach, you can create lots of events, and what the output eventually is some kind of a spreadsheet output, which can then be looked at by the analyst manually, and he or she can figure out first information about malware behavior. Okay, so as I said, that feature is pretty similar to what sandboxes do. There might be one advantage. As I said earlier, if you figure out that in a certain snapshot there's interesting stuff going on, you can go back to the snapshot, look at it, and dig into the details without having to rerun the sample. Okay, now we move on to other features which are a bit more interesting, and then this timeline feature. The spirit or idea of the following features is more to really understand what's going on in memory during time, in these memory traces. And you will see later that the ability to understand that can be quite useful in an analysis. You will see that in the demo. But we first go steps through these features one by one. Okay.
So as there is a lot of data in a memory trace, we thought about different ways to analyze those memory traces. So we came up with visualizations which helps the analysts get a quick overview of the memory traces. And let me show you the first one, which is basically the virtual address space visualization. So we take one process and visualize every memory region of this project. We use colors to represent the attributes of the memory traces, of the memory regions. For example, a red memory region is executable, whereas the green is just readable, and the yellow are writable and readable. Then on top of that, we use layers to annotate the graph further. For example, here you see also the loaded modules and the main module. So then if you find an interesting spot, you of course can zoom in freely. It's an interactive graph. Oh, I forgot one thing. You can also read some kind of behavior of the executable here. So for example, if a module gets loaded during runtime, you will see that also here. And if memory flags get changed, you see a color shift. So let's zoom in on this red rectangle here. And now you see a more detailed view of the whole memory, of this memory region. So here you see now every memory page. And every time there is a small gap between those memory pages, for example, this gap here. So that means that there is a change in this memory page. You can then, of course, use standard tools like a diff tool to find out which byte exactly got changed there. As I said, this graph is interactively. You can then click on every memory region to get different views of them. For example, the standard hex view or a pixel view, which we show later. And you can also export every memory region or even the whole snapshot for further analysis. So as there is so much data in a memory trace and even in just one virtual address space of a process, we try to reduce the data, or we try to reduce uninteresting data as much as possible. So that's where our whitelister comes into play. So here again, that's an excerpt of the virtual address space we saw before. We see here again the loaded modules, or a few of them, namely the kernel 32 DLL. And what we like to have now is some kind of feature which whitelists everything, meaning that we get the result where we can see if those loaded modules are unmodified or if they got some kind of code modifications or API hooks. So every green module here is now whitelisted, and meaning that they are original unmodified modules, and the red bars indicate that there are 2 memory changes in this picture, for example. So here's how we do that. So we have a whitelist, which is basically just a folder containing every single DLL from a Windows installation. And then for each loaded module in a snapshot, we take the corresponding DLL from this whitelist, we relocate it to the exact same position as it is loaded in memory. And then in a second step, we can just simply compare those 2 modules byte per byte. So we not only verify if the module is correct, we also spot any kind of differences. This, of course, introduces some kind of difficulties. For example, the IIT, the import address table, contains pointers to other relocated modules, which are, of course, dynamically. So you cannot easily byte per byte compare them. So what we do now, the solution for that is we just ignore the IIT for the moment, then we do the whitelisting for every module, and then at the end of the whitelisting process, we come back again to the IIT, check every entry, and verify if the entry points to an already whitelisted module or if they are still 0. So this works perfect for the IIT, but there is another difficulty, namely the ORPC sections. They are found in valid Microsoft modules. They are used for object remote procedure calls, and they contain usually newly generated code. So every time, so they got also spotted by our whitelister. So what we do now is we give the analyst a configurable option to just ignore them or to check them anyway, but then he got notified of those changes also. So now we have seen how we can eliminate uninteresting memory regions. What if we have found some interesting memory region and we want to get more information of them? So that's where our pattern matching comes into play. And here we see again the virtual address space of some process, and there is an unknown executable memory region which appears in the middle of non-executable code. So that looks interesting, and we of course want to know what is it and where does it come from. So here is the pattern matcher. We have a source memory region, and we try to match it in every address space of every process, so in the whole memory trace. So the simplest algorithm for doing that would be to compare the source memory region with every memory region in the whole memory trace. This is of course not applicable, as it would not perform very well. And if we also do byte per byte comparisons, we would only find exact matches. But due to relocations and other stuff, we are also interested in finding fuzzy matches. So what we do, I will not explain every detail because of time reasons, but instead of comparing every and each byte, we reduce the memory regions to a locality-sensitive hash. This hash will produce similar hashes for similar data. So we can then compare these hashes directly using the Hamming distance. So, but then we still need to compare each and every hash with every hash of the whole memory trace. So we build a search tree. We then insert every hash in this tree, and so we can just query this tree for similar hashes. So this results in a fast and efficient way to find both exact and fuzzy matches in a huge data set.
Okay, this is the last feature. This is about detecting self-modifying code. Self-modifying code is often used by malware, for instance in packing, unpacking. And the key point is that often self-modifying code regions are the interesting ones because the malware writer tries to hide something. So our goal is to spot these regions of self-modifying code in memory trace. And visually, it looks like that. I mean, it's pretty simple. So if you have a trace here, we just, if you find regions, you're going to mark them with black. To show them where they are. Let me briefly show how we can actually find them. We have, again, an algorithm. It's pretty easy and works pretty well. So what you see here is, again, time axis in this direction, the x direction. What we see here now is the virtual memories, virtual address space of a process. And let's assume just for a moment that we can perfectly detect regions that contain code. That's actually a hard problem, but let's assume we can do that. These would be these light green regions. Then we do, if you can do that, it's actually pretty simple to spot self-modifying code. There are two checks you can do. One check would be here. You see the code region size remains the same, but you would check here is whether within the region memory contents change. This would be self-modifying code because you have code and the contents change. Pretty easy. And the other check would be that one here. You see that the code size actually grows, so we have code that has been somehow unpacked or generated. That's what we do. It works pretty well. The question is, of course, how we can spot these green regions, how we can spot code. As I said before, in general, it's a hard problem, but in practice, a simple heuristic will do in many cases. At least in the cases we have checked, the heuristic worked pretty well. We do actually two things. For each page, we count some characteristic instructions, which are typical for code, and then check if they are below or above some threshold. Okay. And the other thing we do is, of course, depends on the compiler, but we check if we find function prologues or epilogues. And these are our two indicators to check if there is code in a memory page. Okay. And then using these checks, we look for modifications for increase and decrease in memory as shown on the last slide. Okay. We've shown you the 3 or 4 features we're going to use in the demo, which is up right now. We have other features. We have features for crypto detection. We have features for heap sprays and stuff, but we're not going to use them right now, and we don't have time to talk about them. And I think the demo is anyway much more interesting. So in the demo now, we're going to show you how the 3 or 4 features we've shown so far can be actually used to develop an understanding of a malware infection. And our sample here is a zero-axis peer-to-peer bot. And we don't need to know anything about that bot, actually. All we need to know for the analysis for the moment is when the bot installs, it will show this user account control panel. And what it shows actually, it shows that it is Adobe Flash Player. And everything seems to be legitimate. The signature seems to verify perfectly, okay? And the user typically clicks yes because he or she thinks this is Adobe and gives privileges to the process. And what we want to find out now next is, okay, what's going on? And we do that in memory traces and our tools, okay? So first thing we would do is we would do this timeline we've spoken about first. Instead of showing it in Excel format, we've done a simple graph to show it, so it's easier to grasp what's going on. I won't go into all the details, but what we see here from this timeline is files being dropped. We see an install Flash Player X, Google Update, and the MS-ING32DLL, which are dropped on disk. We recover this information from memory. And we also see that there's some relations between processes. So we see process creation. This is the blue arrow from zero access to install Flash Player. And what we see also are these black arrows, which means that one process has a handle open on the other process. Okay. And what is a bit strange here is you see you have a handle from Explorer to zero access, from zero access back to Explorer. And the same thing here between install Flash Player and services exe. So this could be indications for code injections, because you typically need to open a handle on the process when you inject code into it. So this is kind of the big picture we have. So in the in the more detailed analysis now, we're just going to look at these 4 processes to figure out what's going on. Okay. So, demo.
So here we are in a visualization we haven't introduced yet. It's basically the process view of our tool, and it shows every process which was recorded in the memory trace, along with the relationship between child and parent processes. And there are also those blue bars which indicate that those are threads. But we will not use those threads in our analysis yet, but they can be a source of information for other analyses. So we open up the virtual address space of the zero axis. So what you see here is basically a normal layout of a process. You have the main executable in pink at the top, and every loaded module in blue below. So if we zoom in there, we see another memory region, the red one. It's an executable memory region, which we haven't identified yet. So now that we have a hint that zero axis is somehow related with the install flash player, we use our pattern matcher to search for the main executable in the install flash player. So we could have searched in all processes, but for time reasons we limit them to the install flash player, and also just in the user memory now. So this takes a bit of time. I will skip that.
You see, it's a real-time video.
So here you got the list of matches from the install flash player. The reason why there are so many entries in this list is because we search match for every page. So you see also the percentage, so this is like exactly the same thing. So now we open up install flash player to verify the search results. And here again in black are the results. So we see that it found the zero axis main executable in another loaded module. When you then hover over it, you see it's MS-IMG32, which is then basically exactly the same as the zero axis.
So yeah, so we have a couple of demos, and after each demo we just give a brief summary so that we can develop the story and we don't get lost in the story. So what we have established in this first demo, essentially we had zero axis, and we found out that the main image of zero axis is the same as this MS-IMG module DLL loaded by install flash player.
So here we are back again in the install flash player. Now we want to look at the other things. So let's use our whitelister to check every loaded module. So here down below are all the modules, and we don't know yet if they are modified or not. So click in the whitelister, we select the whitelist. It will also take a short amount of time. So here are now the results. You can, again, going with the mouse over it and see the results of everyone. So there are basically 0 wrong bytes in every module, except in the anti-DLL module. So firstly, there is no change, 0 bytes wrong. Then there is one modification, which will modify 7 bytes. And then there is a second modification, and after that modification, only 5 bytes are wrong. So 2 bytes got reverted to the original value. You can then, of course, list the differences. Here, for example, we just have a look at the function which got modified, and it is the RTL exit user process function. We got the name from the EAT, so we don't have any symbols loaded. It's just from the binary itself, from the memory trace. So now we want to find out which bytes exactly got modified. So we zoom in. Here we see again the memory change, the gap between this memory page. We then select the original page, the modified page, and the second modification. And then we do basically a triple diff. So here again you see the contents in a hex view, and there in blue is the modification. So the first window here on top is the original, the first modification, and the second modification. So the original, when we disassemble that, we see it's basically a function prologue like found in many functions of legitimate functions of DLLs. So the move EDI, EDA, so it's basically a knob. This one gets then modified here by the jump instruction. This one is a relative jump, which jumps to the call, and then the call goes to an absolute address. We will see where this absolute address belongs to. So then the second modification will revert the jump to the move EDI, EDI again. And what this does is it disables this hook again. So this is a transient hook, and you will not get that if you had just one snapshot at the end of the execution, of course. So now let's see where this jump goes to, or this call goes to. So we copy the address, put it in the input field and search. So it leads to an executable memory region. If we enable back the layer, the image layer, we see that it is in the MSIMG32, which is 0 axis. So this hook here is used to get the privileges of the install flash player. That showed further analysis, of course. You could, for example, take this address, take the snapshot, and analyze MSIMG32 at exactly this address, and you would get the contents of the API hook there.
Okay, so big picture again. What we have seen, there's a transient hook which appears in this install flash player process. It points into the DLL which has been loaded, which is, by the way, the same as the main image of a 0 axis process. And we have also understood that the whole thing is related to a privilege escalation trick. So next we're going to show, is this a self-modifying code? Okay.
So we are back again in the install flash player.
Is that something?
Mm-hmm.
Okay.
Yeah.
Is it running?
Space.
Okay. So we're back there. So we're going to use the next feature, this is detection of self-modifying code. We turn it on. Let's see what you get from it. So you see here this black region is self-modifying code which has been spotted. It's nice to see that's here in the executable region. So there's some kind of unpacking going on apparently. And the next step is to try to understand a bit better what's going on. We do, again, some diffing before and after, and you will immediately see that's actually a PE file which is unpacked. You see it here, okay. So that's something quite usual. I mean, PE files which are being unpacked in runtime. Let's go a bit even further and try to understand the unpacking algorithm, which we can do visually in this case. What we do now is we use a visualization technique which works roughly as follows. We color code instructions, okay, or groups of instructions, and that's actually the picture you see, this bitmap, and we can animate this bitmap, okay. This is the code region. This corresponds to the code region which is being unpacked, of course. So we can animate it in time, and if you look at it, you see that the colors keep changing, but the structures are the same. I hope you could see that. And what is a possible interpretation of that? So what we can probably conclude from that is that the packing and unpacking is not using any crypto, because this would destroy any structures and statistics in the code. So it's probably some simple linear transformation like XORing, etc., which we could in this case easily confirm by looking at the code further. Okay. So, okay, that's an easy case, but you can kind of visually unpack the whole thing. We kick in this self-modifying code search once more, and we now also search in non-executable regions to see if there is also code being written to other regions. And that's actually what's happening in this case. You see these black bars there in data regions, okay, in heap and stack and stuff. And what's in there? Again, PE files, okay. So we see self-modifying code not only in the executable itself, but also some, where's the build? In some other regions, it's actually summary here. So self-modifying code in the executable region, we could visually unpack it. It's XOR-based packing. And we have more self-modifying code. We don't know why for the moment. We try to figure that out in upcoming steps, okay?
So for completing our analysis, we have a look at the services process, and we have already whitelisted everything. So everything is green, looks fine, no modifications here. But you see already there is a red bar at the top right. So this is also a point where visualization helps a lot. This is an unknown executable memory region. And of course, we want to know now from where does it come from, and that's where we use the pattern matcher again, and it basically shows that there is a 100% match in install flash player again. So remember this gold region here, which is marked black. That's where we found the PE file in the previous step. And now the pattern matcher says us that this is the region where the executable were copied to service exe. So we verify that again by searching again the SMC, and it will of course result in the same as before. So it is this region here again.
So to sum up, we have seen here, we have identified in the previous step this self-modifying code region, which we didn't know where it belongs, and now we could figure out it's actually code which is somehow copied or injected into services.exe. So I think we're going to look at the last process now, the Explorer process.
So again, we have already whitelisted everything, and everything looks fine except for one red bar, which is very small right now, but we will zoom in later on. But let's explore more of this process. So here we see again an unknown God region, which looks very familiar. We saw that nearly the exact same thing we saw in services.exe. So, but let's keep that for the moment, and let's have a look at the API hook which got detected down below. Oh, there it is. It is in the action center DLL. So we again look at the function. This time IIT entry got modified, namely the shell notify icon W entry. So this time we will not see any code, just a pointer. Again, let's have a look at the modified byte. So here it was. We can again, of course, search for this address. And we will see it points directly to the unknown memory region, which we have spotted before. So this memory region will do this hook. You you can then, of course, use that address to disassemble the memory region at exactly this address and find out what this hook does. And we did that, and we saw that it basically removes the action center icon from the taskbar of a Windows computer. That's the icon which will remind you to update your AV, to check your firewall, etc. So the function is still there, but the icon is away and you don't get any notifications. So again, now from where does this memory comes from? We check again with the pattern matcher. We already did that here. So there is again a 100% match in 0 axis this time, not an install flash player. So this comes from this memory region here, marked in black. We will also find it with the SMC detection. So why does this memory region got injected in Explorer, and in the other case, in the services, it got injected from install flash player? That is because you don't need to have extra privileges to inject into Explorer, but you need to have more privileges to inject into services.
Okay, so that's pretty much the outcome of this analysis. I'm not going to repeat that. So I've also seen injections to Explorer. So I think, or we hope the takeaway message is that you can very quickly understand this infection behavior using these tools. It's pretty handy and it's almost automated. And also, as we have indicated during the demo, it also gives you pointers where you could look further to understand the code. What the tool, of course, doesn't do for you is understanding the code. I mean, it just points you where the interesting regions are. But I think that is already, we hope so, it's already quite helpful, actually. So this was for the demo. So the next question is a more technical one. How are we doing this acquisition? How we do recording of these memory traces? And that's Dominic's part again.
So here is an overview of our recorder and its environment. So basically, there is KVM, the kernel virtual machine, tightly integrated into the Linux kernel. It's implemented as a kernel module, and so is our recorder named CAN here. So our recorder hooks itself at runtime to core functions of KVM in order to intercept the running guest and in order to get its memory. So another component here is our writer. I will explain it in a later slide, but basically it writes everything to disk for now. So now there are two questions: when we make snapshots and how we make snapshots. For the when, the triggering. So because KVM uses hardware virtualization capabilities of modern CPUs, we cannot easily intercept the execution of running guest. So in order to do that, we need to wait until the guest execution pauses and gives back control to the hypervisor. Such pauses are called VM exit. So we can do snapshots whenever such VM exit occurs. Of course, we can also trigger artificial VM exits with certain techniques. We will see one of them in the system call trigger. The system call trigger can be used to make snapshots whenever certain system calls occur. We will explain that also in a later slide. Then the other triggers currently implemented are rather simple, although they are very useful for certain scenarios. Let me point out one more thing here. The choice of triggers really matters. So clearly, when you make a memory trace where you trigger every 2 seconds, you will have less information or less transient information than when doing a memory trace where you trigger every 2 milliseconds, for example. So the triggering matters. That's also why we implemented this system call trigger, so we can have snapshots exactly at the moment where we want. So our generic system call trigger injects a small agent into the memory of the guest. This, of course, modifies the guest memory, which in a forensic way some of you might not want to have, but in a reverse engineering way it's not that a really big deal. It gives us great flexibility, so we can decide whether we want to make a snapshot for certain system calls or not. And that way, we only leave the guest execution by a VM exit when we make snapshots. When we don't want to make a snapshot for a system call, we don't need to leave the guest. And such VM exits are really expensive in terms of performance, so we really want to reduce them as much as possible. We then set some model-specific register to use our agent whenever a system call occurs. So whenever a sys-enter or sys-call get executed. And then we basically decide whether we want to make snapshots or not. When we want a snapshot before the system call, we use CPU instructions like VM call or CPU ID. CPU ID can be configured to generate VM exits when called. When we want a snapshot after the system call, it's not so simple. So we use two different tricks to do that, depending on the platform. On 32-bit, we simply set the sys-enter CSMSR to 0. And on 64-bit, we set the RCX register to a non-canonical address. Both will trigger a general protection fall when returning from a system call by either sys-exit or sys-ret. This general protection fall can be then configured in the virtualization environment to also produce VM exits, and that's where we make the snapshots again. So this system call trigger is configurable, so you can decide whether you want snapshot before or after certain system call. And it works really well for both Linux and Windows on 32-bit, 64-bit. So now that it is clear when to make snapshot, let's see how we make snapshots. So for making snapshots, we enumerate the entire guest physical memory, including every memory mapped I/O. This is done by traversing the extended paging table. Those tables are used to map the guest physical memory and to separate those from the host physical memory. By doing that, we keep also track of the state of a certain physical memory page. For example, if they are dirty or if they are clean, since we took the last snapshot. Then the dirty pages get copied in memory and then sent to our writer thread. This way, we increase our performance by a factor of about 10 times because the in-memory copy is a lot faster than if we would write them directly to disk and need to wait until it's written to disk. So this is a little performance trick here. Our current implementation has some limitations. So for now, we can only have 512 megabyte guest memory, but we are sure we can sort them out in future versions. So to sum up, our memory trace engine performs really well. You can interact with the guest during recording, so click on things and such things. It makes snapshots below 30 milliseconds for a snapshot. For Linux, for example, it's really fast, makes snapshots in 3 milliseconds. And of course, this depends a lot on the trigger frequency. If you set 10 system calls to trigger, it will perform faster than when you set 100 system calls to trigger. So it is also operating system independent. That means whatever runs in KVM, you can record. So you can also record whole boot sequences. And we also think it's relatively stealthy because we have minimal to no guest instrumentation just for the system call trigger. If you use other triggers, you have no modification of the guest memory at all. So it is as stealthy as KVM is, of course.
Okay, so let's sum up. We hope we have convinced you that memory traces can be useful for understanding what's going on in the system. We have shown the example where you could understand the infection behavior of malware from these traces. And the other point is we think that it allows to point an analyst to interesting code sections where he or she can carry on manually. I think the subtitle of the talk was Forensic Soundness, or Forensic Reverse Engineering. What do we mean by forensic? That's actually the point. What we mean by that is you can go back any time to a snapshot and look what happened at that time. So when you capture a memory trace, you really get the behavior at the very moment when you take it, and you can go back to essentially all states. Okay, you don't have to rerun the sample, you don't have to redebug it, etc., etc. In that sense, also this technique is kind of a hybrid technique between dynamic and static analysis. Okay, because you can statically analyze the snapshots, and the dynamic part is the snapshotting itself. So concerning the outlook, what we have shown is a rather simple analysis, and we think there can be done more, and that's what we try to investigate in the future. So our vision would be to have kind of a complete understanding what's going on in memory over time, especially in kernel memory, which we don't understand for the moment, but other things as well. And we currently believe if you can develop this understanding, you will be able to spot lots of rootkit and malware techniques. Another interesting line of work would be probably is to correlate different memory traces. Let's say you have a memory trace of sample A and sample B. You try to correlate if there's something similar, to classify them or these things. Okay, so anyway, if you have any questions or ideas, maybe you can ask some questions now. Otherwise, we'll be around at REcon. You can email us, of course. And first of all, thanks very much for your attention.